Welcome, everybody. My name is Ghislain Fourny. I'm with ETH Zurich. And I would like to introduce today our research and actually working product, RumbleDB. This is joint work with Ingo Müller, Stefanie Rimescu, Jan-Berg Kortikis, and Gustavo Alonso at ETH Zurich. So the first thing I would like to say is that RumbleDB is complete. It's publicly released, it's documented, it's free, it's open source, and it's available now. And in today's tutorial, we'll be able to try it out together. So you can actually, even while I speak, go to rumbledb.org. It's just a 12 megabyte jar that you can download. And you will also find in the documentation that all you need in addition to this is a Spark or tar file that you can also unzip on your file system. All right, so what does RumbleDB do? Well, it is an implementation of JSONiq, which is actually Xquery's cousin made for JSON, that runs on top of Apache Spark and over data lake. So what that means is that you can write a JSONiq query, and RumbleDB is going to automatically run this on top of Spark and read the data from, for example, HDFS, but it can also be S3, HTTP, the web, the local file system, Azure, Google Cloud, so any storage system you'd like. It supports reading many formats. The data can be just text that you can parse as strings, JSON, CSV, AVO, Parquet, root, libsvm, and so on. So the vision that we have is that JSONiq is the ideal Lakehouse language that allows you to read your data, even if it's messy, large amounts of messy data, all the way to clean up validation, structuring your data, normalizing it, and feed it into your machine learning pipelines. So RumbleDB does all of that. So the look and feel is similar to what data scientists are used to. You can use Jupyter Notebook and directly type in your JSONiq queries, even with a cluster behind. It's exactly the same look and feel as on your own machine. This is what we use in our courses at ETH with our students. This is the way we use RumbleDB in notably the big data course. So we have Jupyter notebooks for those who prefer it. We can also use the shell, also a command line interface to do it in a batch processing fashion. And there is also a public Java API for those who want to integrate RumbleDB in a host language. So let me now zoom out a little bit and give a bit of perspective on why we are doing that. So I would like to first talk about big data and the advancement in the technology that happened in the database world in the past 2 decades, let's say. So it's customary to define the evolution in terms of the 3 V's, right? Volume, variety, and velocity. So in terms of volume, we clearly have a larger amount of data. So we went from kilobytes, megabytes in the older computers, all the way up to zettabyte and yottabyte. So this is what would be produced by humanity in 1 year, or even since the beginning of times, because what's produced in actually the last 3 years is pretty much the same as before, since the beginning of our civilization, right? So, but just if you compare, we tend to forget that these are really powers of 10 and orders of magnitude, because if you put it in perspective with the size of the universe, it's basically going from the Earth to the entire visible universe in terms of scale. And that's actually something that is quite impressive. So this is for volume. Now let's go into the velocity. So velocity, I like to explain with the evolution of 3 paramount factors: capacity, throughput, and latency. So capacity is how much a hard drive contains. For example, if I look at this, the first commercially available hard drive was in the 1950s. That was the IBM RAMAC 350. It had a capacity of an amazing 5 megabytes of data. The throughput, so the speed at which you can read from the disk, was 12.5 kilobytes per second. So they were called characters at the time, the bytes. The latency is 600 milliseconds because it's time to for the heads to move, and the dimensions were more than a meter. So you see, it was absolutely gigantic. And now, if you go to a closer time, so the currently available largest HDD that I'm aware of is this one. It has 20 terabytes of capacity. Its throughput is 250 megabytes per second, so it's much more than the 50s, of course, and the latency is also reduced. So this is the one that goes down to 4.16 milliseconds. And you can see it's also much smaller. right? So you have to consider the capacity per unit of volume, right? So to consider that it fits in much, much less space than this. Okay, so now we are in big trouble. We are in very, very big trouble. And the reason is that if you compute the evolution of these three factors, this is how capacity evolved. It's now we can store 200 billion times more data in a specific unit of volume. The problem is that the throughput has only increased by a factor of 2,000, which is still a lot, but it's nothing compared to capacity. So it takes much, much more time in order to completely read a disk than it did before. And latency is even worse. It actually only decreased by a factor of 150. And the really big trouble that actually drove all the innovation of technology in the realm of big data of the past 2 decades is because of the mismatch between the evolution of those quantities. So how do you compensate and adapt to the fact that capacity increased much more than throughput? Well, you parallelize. Because if it takes too much time to read the data, you have an input-output bottleneck, you can simply read the data in parallel on thousands of machines. Right? So this is how you fix this mismatch. How do you fix the mismatch between throughput and latency? Well, with time, you spend more and more time idle and waiting for the head of the disk to move in place until you start receiving data. So we can solve that with batch processing. And it's the idea that instead of reading small quantities of data, we try to read a batch of data at the same time, a larger batch, right? So this also justifies that we have blocks on local hard drives of 4 kilobytes instead of reading bit by bit. But we also need to do that at larger scales. And of course, in that case, the blocks we are talking about are not kilobytes, but megabytes. Typically 128 megabytes is actually a very common size for a batch, right? So parallelism and batch processing. And variety, the third V, has to do, it's very familiar to a lot of you because there's a lot of XML and JSON aficionados in the room, I assume. It's the idea that this data shape that was very popular in the 1970s and that gave birth to relational database management systems with Edgar Code's data independence idea is no longer the only one. And by the way, this doesn't date back only to the 70s. This is actually thousands of years old because I think I have it on one of the slides that follow. There are even clay tablets that we found that have relational tables, which is quite impressive. Of course, we have text. This is also quite old. But trees are one of the shapes that became quite popular in the past 2 or 3 decades with XML and JSON, because this is what it is. XML or JSON is a tree in terms of data model. All right, and this corresponds in a way to denormalized versions of the tables, right? If you denormalize tables, you even drop the first normal form, then what you get is a tree with nested data. And then we also have other shapes such as graphs with graph databases like Neo4j, RDF, triple stores, and so on, and cubes with OLAP and data warehouses, right? But I'm not going to focus too much on them, as you guessed today, more on the trees that are denormalized tables. So if I speak of JSON in particular, why does it play a role in the natural evolution of databases in terms of variety? Well, if we pick all databases, we love normal forms, right? So this is what we teach on the bachelor's level curriculum at almost any university. You have to construct and build your schema in your relational database in the way that you avoid a few issues such as update anomalies, delete anomalies, and so on. And how do you do this? You normalize your data. So you try to nicely separate your data into tables and you put together the data that makes sense together. And that way, if you update the data, you don't have consistency issues in your database, right? So there's plenty of normal forms. The problem of this, and this is what we became aware of in the 2000s, is that the real world isn't like that. The data isn't always perfectly structured as in relational databases, and also joins are actually quite expensive. Of course, we have efficient algorithms, but nevertheless, it's much more expensive than other operations such as selection, projection, and so on. All right, so what happens? Data used to be flat and homogeneous in relational tables. And now we are looking at nested and heterogeneous data set. And typically, this is JSON, XML, and so on is exactly that. So we have nested values, we have tables in tables in tables, just like the Inception movie. We have missing values. Not all records might have a value for all attributes, and we can have invalid values, right? In a JSON or XML data set, you could have different types. And you can also have extra values. You can add fields, especially in data that hasn't been validated. You can have extra fields that some records have, but not all of them. And of course, the key things here is to understand that this is just coming down to a collection of trees, right? And this is what you find in any document store, XML database, JSON database. In the end, you replace the tables with collections of trees, but in the end, it's based on this rationale. Okay, so we have data sets that are available out there that can have billions or trillions of records. And an example of such data sets use the JSON format with one JSON object per line. So this is this is one example of such file, right? Of course, we have other formats that are much more efficient, binary formats when the data is partly structured. But I think it makes a lot of sense today to focus on JSON lines because the idea is actually the same as for many other data formats, right? So an example of data set that we love to use in our course because it is heterogeneous, it is nested and so on, is the GitHub archive data set. So we have a data set with 2.9 billion events. So each event is a JSON object. It's 7.6 terabytes of data in there. So you see that's a lot of data. It fits barely on your laptop. Actually, it doesn't fit on some laptops because especially if you have an SSD, the size is much smaller than that. 10% of the paths have mixed types. So you very often have at the same location in the object, here an integer, here a string, here an array with an integer inside and so on. So this is heterogeneous. It wouldn't fit in a relational database for this reason. And if you consider the attributes, even though each event has less than 100 attributes, if you look at all events together, there is more than 1,000 attributes. So here you see also the extra attributes, missing attributes. So it's highly heterogeneous. And you can also see the nestedness right there with objects in an array in an object. And of course, this corresponds to a nested table, right? So an array of objects that look similar is basically a nested table. So it's not in the first normal form. So what happened then with the realization that first the data has more variety than before, so it's not necessarily available as tables. It can be available as a collection of records that can be pretty much anything. And the realization that we have this impedance mismatch between capacity, throughput, and the latency. So it forces us to parallelize and to batch process. And this is exactly what gave birth to technologies that were invented recently for data processing in clusters of machines. So the first data processing framework is extremely simple. It's MapReduce. It's based on a simple two-phase model where you process collections of key value pairs. So somehow you make the data fit as key value pairs. Then you have a mapping phase, then you shuffle the data around, especially for grouping, aggregating, and so on. And then you reduce, which is again, actually just like the map phase, but it's just that now you're processing the data in buckets based on the key, right? So one bucket at a time. But then we had a newer generation of technologies that generalized this approach to not just these two phases of map and reduce, but a whole graph of flowing data, technically a DAG, a directly acyclic graph, which basically means that there are no cycles, right? So dependency graph, there is a flow of the data in elapsing time. And this is what Apache Spark is doing. It allows you to process data in such a generalized way. The first class citizen in Spark is called an RDD. It's a resilient distributed data set. It's basically a collection of whatever you want. It can be a collection of JSON objects, a collection of strings, a collection of XML nodes as well. So anything you want, right? So it's a partitioned collection of values because this can be very big. It can even be dozens of terabytes, hundreds of terabytes, but it's partitioned and distributed over your cluster in your data center. And the idea is that you can create RDDs like that by reading your data from Amazon S3, from HDFS, or even from your local file system on your laptop. You transform the data, you can map, filter, there's a lot of primitives, and finally you take an action to print it on your screen or output it back to some different backends. And there's a whole menu. It's like in a restaurant, you have a whole menu of transformations to pick from: map, flat map, order by, filters, if with index, group by. These are just a few examples of that. It's like a big Lego game. And then you can build your data processing job with all these primitives and get Spark to do whatever you want to do with your large collection of messy data. So this is an example. In that case, it's Scala, but it can be Java, Scala, Python. There's many languages available, where here we create artificially. Of course, here we create it in memory, and then we parallelize it. Of course, this is small. This creates a first RDD. Then we flat map that RDD by splitting the strings according to spaces. So this is what we get, right? And finally, we have this action that materializes the counts by values, and this is something you can print on your screen, right? Of course, it only works if it's small. If it's too large, then you either have to take a limit on what you want to see on your screen, or you can write everything back in parallel to your cluster. So as a consequence, an alternate way of processing data has emerged. So in the 1970s, with the first databases, there was the idea that you import your data in your database, then it's stored in an optimized format, and then you can query your data with a language within that ecosystem. But with Apache Spark or MapReduce and all these cloud storage technologies like S3 and Azure and so on, the idea is that we have a data lake. You just drop your data in there and worry about looking at it later, processing it, validating it, and so on. So it's more for read-intensive and batch processing jobs due to the reasons that I told you, because it's a much larger scale, but you don't have to ETL your data, right? So you don't have to go through the effort of ETLing. Of course, querying will be a bit slower, but you can go right away, start right away with querying your data, right? And this is the approach also that we take with RumbleDB, that we have a data lake where your data is, and you read it in place from this data lake. All right. Now, there is one thing that went backwards, because Edgar Code in 1970 invented this concept of data independence and the concept of modern relational databases, with the idea that you can expose the tables to the end users and hide the underlying physical storage from the user. This is called data independence. So it could be a clay tablet. This is the one I promised I would show you, right? It could be a clay tablet, maybe a bit slower, but this is how it was done thousands of years ago. Can be a more modern spreadsheet, not recommended though. It's better to have a database system. It can be your local drive. It can be a cluster of machines as well on which you run that. And even DNA. There are even groups of researchers today that manage to execute relational queries directly on top of DNA, where the data is encoded with nucleotides. Okay, but the problem is that I will show you now that with Apache Spark and all these technologies, we took a step backwards, because now we are breaching this idea of data independence. We are exposing a lot of things to the user that we shouldn't be exposing. And of course, the Spark team realized this. And this is the reason why they introduced DataFrames in their system, with the idea that if you import data like this from your data lake as just a flat collection of, in that case, JSON objects, but it could be XML, could be anything you want, and you notice some structure in there, you see there's always first, last, and so on countries. So it's tempting to interpret that as a table, which means that you have a collection of rows and they all share the same attributes. So in essence, you can import this as a table like that, a relational table. This is what's commonly called a data frame. And then you have all these APIs that allow you to process data frames in that way. And Spark was augmented also with an API like that, right? So it can process very large quantities of data stored in data frames like this that are highly structured. And that way you can actually directly import this sort of data in your data frames. And then, of course, what you can do is go ahead and use data frame transformations in order to process the data, but even better, you can use SQL. So now you can use, it's the local dialect, it's called Spark SQL. So you can just type SQL and it will automatically convert that to the data frame transformations for you. So it seems that we have now gained back data independence in Spark, right? So problem solved? Well, no, we think the problem is not solved. And in order to see why it is not solved, It suffices to see what happens where the data isn't that structured. For example, here name is a string, not an object that is composed of first and last. What happens is then that if you attempt to open that in a data frame, you will see that it will create a column of type string because it has to have a type. You don't have variants like you have in other companies. I'm thinking of Snowflake, for example. So here you have the type string. So it means that it's stored everywhere as a string. And here too, it's not a JSON object. It is really the serialization as a string of a JSON object. So you're basically throwing back to the user the burden of having to parse this back as JSON. Right. So this is going backwards, right, in terms of data independence, because you're expecting a lot from the user that they shouldn't be doing. The same happens here in the case of a string or an array. And of course, here we have serializations of arrays, right? There are strings, and here we have just a single occurrence of number right there, and then it forces an additional attributes with nulls everywhere. And you also see it in the language, because then there were extensions of SQL, for example, the explode function, in order to explode these arrays right there and map that back to an exploded table. We also have dots. So a lot of approaches add dots to the language in order to navigate objects. So this is how, if you have an object here, of course, it doesn't work if it's a string, but as I showed you before, but if it's an object, then you can nicely also navigate down in there, right? So the limitations of the data frames become very clear when you notice that it's incredibly complicated to write the SQL, that it was supposed to be a simple language, but you see it becomes very complex. And it turns out that you can also get extremely complex queries, even though the query is very simple. Here we are looking for the top committers of each event in the GitHub archive. And this is how complex writing this in SQL is. But with a language that makes more sense, and that's the case of xquery, which is the W3C standard. JSONiq shares 99% of this DNA with xquery. You can do it in just a few lines like this, right? So the motivation behind JSONiq when it was first designed is exactly that, is that xquery is a language that's not in fact specific to XML. It's a generic language that allows you to process heterogeneous and nested data sets, right? And XML is an example, but it can be also JSON or JSON-like formats, right? All right, so let me introduce you to JSONiq. I know some of you are probably familiar with xquery, so you will be familiar with the overall paradigm, but there's just a few differences. It's like, we call it the JDM, the data model. It's called XDM in xquery, so we can have atomic values. And here we support almost everything supported in xquery and XML schema, including date, times, binaries, and so on and so on. Not just the JSON string, number, and booleans, right? So the rich type system that we have from the XML world and that we reuse almost as it is. Then we have objects, we have arrays, and we have functions, because we also have the function items from the xquery 3.0 standards that are also used in JSON. They make especially sense for machine learning, but I'm not going to focus on them today, right? What we do not have, however, right here is XML nodes, right? Because we focus on JSON-like data formats. So the idea is that sequences of items, that's exactly the same terminology as in xquery, allows you to cover the entire spectrum of highly structured data sets with the empty sequence of one string, sequence of numbers, boolean, structured data, but also here fully unstructured, because the sequence of items can also be a sequence of anything, even mixing different kinds of items with each other, right? So it's a functional language as it should be. So you see it looks a lot like xquery, because it's really just xquery minus XML plus JSON. It has the flower expressions that with which you can do and simulate emulate the relational algebra with selection, projection, grouping, joins, or even fully generic, because it's even more flexible than SQL, right? So this all comes from xquery, the flower expression. You can even use it to join with for where, right? And in Rumble, we also optimize and detect these joins so that it's processed efficiently at the Spark level. You can have left outer joins with the allowing empty, that's also from xquery. And you can denormalize your data in this way. Of course, here it's done the JSON way, but you can also do the same with XML, right? Using XQuery, it's the same idea. You can denormalize your data by nesting data inside. All right, so how does it get executed by RumbleDB? So the idea is that we switch between local or cluster execution. So for example, when we have an empty sequence, or it's always an empty sequence, then it's just a method call that returns null, right? If it's at most one item, we can also detect this statically in the program. It's also a simple method call that returns an item. If it can be several items, sequence of more than one item, because in XQuery and JSONiq that's the case, then we use Volcano iterators. So it's basically open, has next, next, close, and so on. Internally, of course, the user only sees that. And here, the same, it's a bit more complex, but it's the idea that we implemented every expression in that way using Volcano iterators that automatically execute it. And again, this is all the user sees. The rest is all hidden. It's just the implementation, right? So now, when I say local, I either mean local on your laptop, because you are not using anything in parallel, but it can also be local on the cluster, because you might be executing that billions of times for each record in a parallel data set. So this can also happen on the cluster, but inside each machine on the cluster. So now what happens if we try to open a data set? So for example, it's a JSON lines file, right? That looks like this. What we do in RumbleDB is that we create an RDD, resilient distributed data sets, where each object here is parsed as an item. It's polymorphic. It uses the Java polymorphism. And we have an RDD of items, right? It can be then distributed over the entire cluster. This can come from HDFS, from S3. So it's automatically created in parallel over your cluster, right? Now, when we navigate, we are just mapping that all in Spark to flat map, in that case, transformations, including a UDF. The UDF is used to pass all the arguments and parameters of the transformation, right? And that includes sometimes parsing compiled expressions of JSONiq so that they can be executed on the cluster, right? So here, that's an array unboxing. That's also done in parallel on the cluster. Then we also have aggregation functions like distinct values. That's also from XQuery that is just mapped to a distinct transformation on the cluster, right, on Spark. If the data is highly structured, there are other formats where it's highly structured, and it's directly opened as a data frame. So then Spark will know that it has all of these columns and it has the types that are known. And of course, then we can navigate it using Spark SQL internally. Right? So we map JSONiq to Spark SQL. So as a summary, for heterogeneous sequences, we map them to RDDs of items, which is polymorphic. And if it's homogeneous, then we map it to data frames directly. And this is done seamlessly. The user doesn't see the difference between the two. They will just notice that this is faster when the data is homogeneous, and it's a bit slower if the data is heterogeneous. Right? So what happens now with flower expressions? How do we map them? Well, here it's interesting because we are able to do that purely in Spark SQL and using data frames. And here's why. You might remember that flower clauses are actually streams of tuples. What that means is that, for example, if I open that file, the JSON file persons, then this is what I get. So as maybe as an RDD. But then if I start iterating, what I can create is a table with one column, because it's a stream of tuples. It's a tuple stream. Where the variable person is associated in turn with items. So conceptually, it's a table with one column. And this can all be done in parallel on data frames. So now if I have a for clause, then I just add a column because there's a second variable binding. Then there's a where clause, which can be implemented as a where in Spark SQL. So you see it's all working on that data frame that contains the tuple stream. The let clause is adding one column right there. And finally, when we return, we map it back to an RDD like this, right? So again, there are several execution modes. We can do it as I described in parallel using data frames automatically, and that works on billions or even trillions of variable bindings of tuples. Or it can also be executed locally if it detects that it's small enough. So it's a Volcano iterator model where we just use open, next, has next, close, and so on the tuple streams, right? We just then process them sequentially and locally. So it means we can have flower in flower in flower. The outer flower might be executed in parallel, and the inner flower is going to be executed locally on each machine, right? But for the user, it's fully transparent. So now if I get back to the expressions, we have, as I told you, the direct method calls, the Volcano iterators, in that case, RDD transformations, because the data might be heterogeneous. If the data is structured, then it's all data frame transformations, you see, but the syntax looks the same. It's just the way that it's implemented that's going to be faster. And in some cases, we can even map that to natively to Spark SQL. So it's even faster, right? But to the user, all they see is the same language. So all JSONiq. So the way that the execution strategy is chosen is that we parse the query, we create a static context. That's also all part of the xquery standards. We do the static sequence type inference, also following the xquery standard, static typing feature. We determine the execution modes and we compile to a runtime iterator tree when we are done. And now it's all chosen and decided what is on the cluster, what is in parallel, what is in a data frame, what is in an RDD, what is local, and so on. So you see what we get is basically this. It's this query is mapped to this tree, and you can see all the way that the execution modes are indicated there, but this is all hidden from the user. For example, this is going to be done in parallel. This is going to be done locally, but on the cluster, on each machine, on each item that comes from the tuple stream and so on, right? All right, and you see that's another example where you can see that this query right there is automatically going to be processed using RDDs, and then finally with a push down of the sum aggregation. So all of these methods right there from the xquery standard work on sequences of billions of items. From a performance consideration, our goal was to be not slower than other systems that work in a similar way, like DB, Spark SQL, VxQuery, and so on. So we compared with other systems. Our goal is to be more productive, to increase productivity, but without a loss of performance. And so this is an example. You can look at the original paper if you're interested in more. But we compare really nicely with the other systems, which shows that this is working. So ongoing work is machine learning library. I'm going to say a few words about that. We keep implementing missing features, but now we are in a really, really good state. We almost have all the functions of xquery 3.0 except XML implemented. We also did a few optimizations, especially the joins, for example. We now have schema validation with the JSON schema language, which is inspired by XML schema that also imports a lot from the XML world into the JSON world. So then that's with this schema language, we can define data frames with the compact form of JSON. And finally, we gather a lot of experience from other universities that started using RumbleDB in their teaching. And we keep working on the integration, especially to make it usable by non-computer science students. So, for example, from digital humanities, or even we teach big data for engineers that is for all other departments of ETH than computer science. And so far, we have good feedback. So just to finish, a few words on machine learning. Here we have a Lakehouse system. That's the idea that we have the data lake, and we can store structured data, semi-structured data, unstructured data. And then with the integrated system, we can do business intelligence, generate report, data science, machine learning, all from the same system. If the data is structured, it will be automatically faster. If it's semi-structured, it seamlessly adapts. So this is the idea that was developed in the CIDR conference, which is where innovations in databases are presented. And this is going from right from this year. What we think is that xquery / JSONiq, it's really the same idea, are the perfect candidates for Lakehouse systems like this. So for example, if we have the ability to define types in the language, that's already implemented in RumbleDB. That's a JSON schema that defines this type. It's automatically mapped to a data frame schema internally. And then you can use, this is also from the validate expression. We try to stay very close to the xquery standard here. So validate type local product by country, except we do it the entire sequence at the time. That's actually an extension. And then we create that data frame, right? So this is how we can create these data frames either from structured data or validate it manually from JSON data, that we end up with something that is highly structured internally. And based on that, we can use machine learning. So you see that's an example here where we define a type, and here we assemble a vector of features in machine learning. We use here the k-means estimator and then we can generate a model, and with that model, which is actually a function item, we can generate the predictions, right? So this is what it returns, and you see the prediction right there. But you see that it's done with so few lines of codes, this whole thing. So it works quite well with machine learning. So I'd like to thank all our contributors. These are all the students, PhD students, postdocs who have been working on the projects. So you see a lot of people who are involved in there, and now it's in a good state. We also started to execute as many tests as we can from the test suite of X-Ray 3.0, 3.1. We are trying to work for all the tests that make sense for JSONiq to adhere to the X-Ray standard as much as we can, and we continue typically to do a release every 2 months. We are trying to keep this rhythm. Right, so this is the end of the presentation. I'm around. I'll be around also for questions, and maybe we can also try to install it if you want to install it now on your laptops. To get you started with RumbleDB. So thank you very much, and see you live in just a few seconds.